Hello and welcome to the next topic. Next topic being resistor networks, the properties of groups of resistors connected together with wires. We'll start by doing a quick revision of the basic theories that we're going to need to analyze these networks. The concept of equivalent resistance, an important one, will be introduced, and then the problem, what we're actually trying to do. And that will be enough for the first of these short videos. So, revision of Ohm's law and Kirchhoff's current laws, the three basic laws of circuit analysis. Ohm's law: the voltage across a resistor is equal to the current flowing through a resistor times the value of the resistance. Kirchhoff's current law: the sum of all of the currents flowing into a node is zero. Bearing in mind that this includes the currents flowing out of the node, we just count them as being negative currents flowing into a node. And Kirchhoff's voltage law: the sum of all of the voltages around a closed loop is zero. Perhaps it would help if I just drew some quick diagrams to make sure that everybody has got these three laws clear in their mind. First of all, Ohm's law. We have a resistor like this. It has a value of R. There is a current flowing through it. I'll call that I. The voltage at this side could be V1. The voltage at this side could be V2. Ohm's law tells us that V1 minus V2 is equal to I, the current flowing from 1 to 2. Sometimes I write that as I1, 2, just to make sure that I've got the current going in the right direction, times R. And I usually write V1 minus V2 as delta V. The difference in the voltages across a resistor is the current flowing through the resistor times the value of the resistance. And that, in a formula, is Ohm's law. We then have Kirchhoff's current law. Supposing we have three currents going into a node in the network, I1, I2, and maybe a current coming out of the node, I3. Kirchhoff's current law says that if we consider currents flowing out of the node as a negative current flowing into the node, then the sum of all of the currents flowing into the node must be zero. So in this case, we would have I1 plus I2 minus I3, because that's a minus, equals zero, or in other words, I1 plus I2 equals I3, which is the other way of thinking about Kirchhoff's current law. The sum of the currents flowing into the node, I1 plus I2, is the current flowing out of the node, I3. And finally, Kirchhoff's voltage law. Kirchhoff's voltage law says that if you have a set of components, like this perhaps, with a voltage source here, so there is some current flowing around it, then that voltage, if I called this, say, V1, this V2, and this voltage over here as V3, the voltage that I go through in going from here to here, which would be V1 minus V2, plus the voltage that I go through in going from here to here, which would be V3 minus V1, plus the voltage that I go through going from here to here, which would be V2 minus V3, that must be equal to zero, which is fairly obvious. If you just expand out these brackets, you'll find that that minus V2 cancels with that plus V2, that plus V3 cancels with that minus V3, this plus V1 cancels with that minus V1, and you're left with zero. So, those are the three fundamental laws of circuit analysis, and we'll be using each of them to solve the problem that we have in these particular set of videos. Now, the concept of equivalent resistance. The concept of equivalent resistance says that if you have a network of resistors like this, all connected up together, with one terminal X and one terminal Y available to connect to other points in an external circuit, then that lot behaves just like a single resistor there with a value which is called the equivalent resistance. So if you built a circuit with these resistors in it and replaced these resistors with this single resistor of the right value, then the rest of the circuit would behave exactly the same. Is that always possible? Does a set of resistors like this behave like a single resistor? Well, we can check that. We'll have a look and see what it does in the simulator. There's an example that you can load in, if you like. Under File I/O, there's a preset called, where is it? It may be called something different by the time you have a look at this, but at the moment it's called Resistor Network A. There we go. Now, a set of resistors like this, the voltmeter here is showing the total voltage across that set of resistors. That's the delta V. The ammeter here is measuring the current, the total current that emerges out of this network. If all of these resistors was going to behave like a single resistor, then we would expect the voltage across this network to be proportional to the total current flowing into and the total current flowing out of the network. Then it would obey Ohm's Law. If it obeys Ohm's Law, then we can replace it with a single resistor. So, is the voltage across this lot proportional to the current flowing through it? We can add a point here, change the voltage across it, see how the current changes, add another point, keep on doing that with different points. Get bored of that, stick it in automatic mode and just fill in all the gaps. And what we see is, yes, all of these points lie in a straight line, which means that the current flowing through this network is proportional to the voltage across this network. In other words, it behaves like a single resistor. All we need to do is work out what value of resistor would give you the same current flowing through for the same voltage placed across it. And that is the fundamental problem of resistor networks that we're trying to solve. What value should this resistor have in order that the same current would flow through it for the same voltage difference across it? Right, that's enough for this video. Next one, we'll start looking at some simple cases, and then in further videos we'll build up to being able to analyze this whole network and some rather more complicated networks than this as well. See you in the next video.